Now we move on to other variations on the well-mixed room model. So the first equation that we looked at, we assumed that the generation rate G is constant, and that is the constant emission version of the well-mixed room model. But there are other versions also. So the generation rate does not need to be constant. In fact, most real life situations are where the generation rate changes with time. And there are a couple of examples that we look at when we have what is called back pressure. So as contaminants, especially if we have a volatile solvent in a room, especially if we have volatile solvent being emitted into a room, then as the contaminant concentration increases in the room, and the room is getting to be more and more saturated, but hasn't yet reached saturation level, the molecules in the room air start to exert a back pressure on the source itself. And so the generation rate is slightly decreased from what it would be if it wasn't reaching saturation. So this is the back pressure model where we have G as a function of time is equal to G0 times 1 minus the concentration in the room air as a function of time divided by the saturation concentration. And this is, a useful thing to keep in mind, although we are not going to spend too much time exploring this particular version. What is of greater interest is the third variation, which is the exponentially decreasing emission rate, where G of t is equal to G0 times e to the power minus alpha times t, where the alpha is the emission rate constant or evaporation rate constant with units of inverse minutes. So the exponentially decreasing contaminant emission rate applies to several common processes. So let's say we spill a small amount of solvent onto a floor or a surface, and the vapors start evaporating from the solvent surface. And after some time, all the solvent has evaporated and there is really nothing left. That is a scenario where this exponentially decreasing contaminant emission rate function would be very useful. Another common process is the emission of a minor constituent of a liquid mixture in a small tank from a small spill of solvent. And a third very common scenario is the off-gassing of residual fumigants such as ethylene oxide or methyl bromide, where you might have fruit that have been sprayed with fumigants such as ethylene oxide, and the ethylene oxide then slowly off-gasses from the surface of the fruit and then eventually is all gone. So let's look at it mathematically. So if we have a small spill of a liquid, a certain mass of some solvent has been spilled on the floor, so m sub 0 is the initial contaminant mass that was spilled on the floor. And as soon as it's spilled, it starts evaporating. And so m, as a function of time, is the contaminant mass remaining in the source, remaining in the pool of liquid that you spilled as a function of time. And so it is decreasing exponentially according to that exponential term. So that is the rate at which the mass in the pool is decreasing. And it turns out that that is, in fact, the rate at which the mass is going to be emitted from the source as well. So if you know the mass as a function of time, m sub t, then the rate of emission, which is the first derivative of the mass, that is given by the mass emission rate, g's of t. So this is alpha times m sub 0 times the exponential term. And so the initial rate at which mass is being emitted from the source, g sub 0, is the emission rate constant alpha times the initial mass of contaminant spilt as a liquid. So we can, again, set up the mass balance equation as before. The only difference now is that the generation rate is not constant, but is exponentially decaying. And the reason for this exponential decay in the emission rate also is clear. So when we have the initial spill, the rate of emission is the highest. And as the mass in the spill decreases because it's evaporating, the rate of emission also decreases because the amount of the liquid pool is decreasing. And when we set up the mass balance equation and do the solving of the differential equation, and I'm going to skip over all those steps, we end up with the final solution as shown in this equation at the middle of the page. C's of t is a constant term at the beginning, and the constant is alpha times m sub 0 divided by alpha times v minus q. And then we have a difference of two exponential terms. So in this case, it's a little bit harder to just look at the equation and predict what's going to happen. But we can, again, think about it physically and try to predict what might happen. So as I described to you earlier, we have spilled some liquid, and the liquid pool is diminishing with time. And so the rate of emission, and eventually the pool is completely gone. So there's clean air coming through the room and purging or exhausting the contaminant from the room air. So we can see that in the beginning, when the spill volume is still large on the floor, there will be an initial rate of increase that will be fairly large, and the rate at which the concentration increases will be high, and it'll reach some maximum. And at some point, all of the liquid in the pool of liquid that is spilled would be gone because it is all evaporated. And after that point, we can see that there is no more generation, and we are just going to purge the room of the contaminants. And so what that means is once we have reached a peak concentration in the room, the concentration is going to decrease with time until the room is completely purged of all the room air. And we can argue this out just by imagining what's going to happen if you have a small spill in a room. And we don't necessarily have to look at this equation. But if we do program this equation into an Excel spreadsheet and put in values of alpha and q and v and so on, we get a profile of concentration with respect to time that looks very much like we imagined it would. So after the spill, the concentration in the room increases rapidly and reaches a peak. And then after that, all of the contaminant in the spill has evaporated and then been purged out of the room air as well. And so there is an exponential decay in concentration over time. And eventually the room is completely removed of contaminant in the room air. So what we have discussed so far today is the well-mixed room model and its applications to different scenarios and some of its variations. So we studied several things. One is there are two terms in the well-mixed room model. The first one describing the rise of the concentration in the room and when it reaches an asymptotic value or the steady state value. The second part of the equation, the well-mixed room model, is also known as the purging equation. And the purging equation describes what happens to the room air concentration when there is no source generating contaminant in the room air. And we discussed these two scenarios for the case when the emission rate, G, is equal to some constant value. The second thing we studied was when the generation rate or emission rate is not constant but is exponentially decaying with time. And this can be applied for scenarios such as a small spill or fumigants off-gassing from vegetables and fruits. And so these are the scenarios for which the exponentially decaying generation rate would be applied. In the next lecture, we'll be studying a more complicated model called the two-zone model or the near field, far field model.